Okay, so you've had already a lot of physiology on the peripheral and pathophysiology on the peripheral. And now we would like to move on to the central disorders and the central physiology. And I can say it will not get easier for that part. But still, I recognize you are not physicians. Most of you, you're not specialists yet on the vestibular system. That's going to come. I want to just teach you a few of the principles behind central vestibular processing and show you some examples on what happens if these central systems are affected by pathologies. Essentially, what you already saw is that the peripheral vestibular system sends in inputs to the first hub, which is the vestibular nucleus in the medulla, and from there you have connections to the eyes, to the spinal cord, to the cerebellum, in order to guide your eyes, your posture, and all your movements. But if you like, this is mostly what the reflexive movements are about. It's kind of the hardware of how to keep balance and how to keep stable gaze. But of course, it's not about perception or any higher vestibular functions. And therefore, of course, there is more than these infratentorial networks, but there is also projections which run up to thalamic cortical levels. And can say that knowledge of these networks, if you were thinking about the other sensory systems, Archimedes know that 2,000 years ago, there is 5 senses, that was not a miracle. And guess what? When the vestibular system was recognized as being an independent system, this is not more than 140 years ago. And even in the 1990s, they asked, is there any central cortical vestibular representation? So we can say that this knowledge is not older than 25 years. So you can say you're working on a very young discipline if you're going to the central networks, but this is also the fun part of it, because there's a lot to discover. And of course, the start for discovering it was we had new imaging techniques, we had new technologies to decipher these networks. After all, just conceptually, it's clear that if you perceive vertigo, this is a cortical sensation, of course. It's in your mind, it's not in your brainstem. Second, of course, you may recognize that the vestibular system is not just guiding your balance and your eyes, but it also guides our. That is when Hans Stracker, who was a Munich basic scientist and unfortunately died 2 years ago, said, the vestibular system started to evolve when we got detached from the ground 300 million years ago and started to move freely. You had to align yourself relative to the environment. And therefore, some of the more hidden aspects of the vestibular central processing is not just perception, spatial orientation. It's also the feeling of yourself against the environment. How do you know that this is the border of your body if nobody touches you? It's also part of your internal perception, which is partially guided by the vestibular system. And these higher subtle vestibular functions probably is what we're about to detect more and more in current research on the central systems. And just one few comments on the basic principles of these projections. So what you already heard is this is the vestibular nuclei, and you have the projections to the eyes. Basically, we covered this. But there is also upcoming projections, and one basic principle of it is that the vestibular system works as a bilateral system. It's a bit different maybe from other systems because you can see with one eye. Perfect. But it's much more a relative information of both sides than an absolute in the vestibular system. It works like you're weighting out both sides. And essentially, this organization is reflected in the anatomy. You have this kind of bilateral projections. You have a rope ladder system where this always crosses over in order to give you a global percept of your movement and your environment. That's also essential. It's not that you can have a percept of your motion for left hemisphere and the right hemisphere, It would be schizophrenia. that you have to have one global percept of your motion, of your position in space. And this is only possible if both hemispheres talk frequently and exchange. And therefore, we have these rope-wise systems of projections. Of course, still we have some functional differentiation in these kinds of projections. This is quite recently published last year with Julian Conrad. And just to give you a small insight on what you can do these days to decipher these projections, which we did is we took patients with a strategic stroke, for example, collineal stroke, and then you can measure signs of a vestibular symmetry, which is, for example, your percept of verticality. You have a perfect percept of verticality, but if there is a lesion to graviceptive pathways, this percept tilts over and you can measure it easily. This is an indication that the stroke affected somewhat the upcoming projections of the graviceptive systems. And then what you can do is then do lesion symptom mapping, and you end up with a statistical estimate of where the core of these lesions is. And with that, you can go to connectome analysis. So there's data available on healthy connectomes. You project it in, and from there you can estimate where these lesions project to. And you have an individual estimate and a groupwise estimate of these networks. And what you see here is we could show there is top projections, and there is also down projections to the brainstem. And it seems there is a functional differentiation of those projections which are crossed and uncrossed. And we'll come to that a bit later, where the main hub of projections in the cortex would be. Because that's what also came with modern imaging. You could stimulate the vestibular system in the scanner, and you could see where the brain activations are seen. You can do that with galvanic, with caloric, with WAMPs, where you've heard. And the common denominator in these networks is actually you always see an activation pattern which kind of bundles to the insula. The insula is where those brain lobes folded in, and actually this is the part of the brain where most of the primary vestibular informations converge to. And of course, there's been meta-analyses on these kinds of data. So they were having different imaging studies pulled together, and with that you end up to have one main spot, which is the so-called OP2 region, as a supposedly primary vestibular cortex. This has been questioned a lot, of course, and because your vestibular system only works in conjunction with the other systems. We have to have visual and vestibular inputs and proprioceptive inputs in order to get a overall percept of emotion. And therefore, it's been so that it's mostly a multisensory interactive network, not just that one region which represents it, and it works in close conjunction with other cortical areas of sensory motor processing. And this is similar to the monkey studies, if you like, which have been done in the 1990s by Goulden and Grusser and so on. They did do electric mapping to see where you have evoked responses to vestibular stimuli. And they came up with a more extensive network, again, of these insular lateral sulcus representations, but it was almost all over the brain. And it is similar in these human studies. You have projections to other sensory systems, to the cingulate, to the hippocampus, so it's quite extensive. And again, this is what Hermann told you. The vestibular system was early, so it was connected to all different kinds of networks, which eventually differentiated along evolution of species. And this is why the vestibular system has a lot of implications for different processes in the brain, which we may not easily pick up. For example, emotional processing. Everybody knows that if you have an acute vertigo attack, you're quite in a bad, emotional, anxious state. And this is because the vestibular system closely projects to emotional systems. Can take it vice versa. So why do kids stop crying if you shake them? No. There's been even a nice Australian study to show that, if you shake them in a certain frequency range, then they stop coming. That is probably a coupling of vestibular and emotional. It may be an evolutionary strategy, because if you have, the monkey baby and the tiger is behind you, with the frequency, it's still just fine. Otherwise, not prone to survive. Anyways, just to open your minds a bit, we're not talking just about perception, but a lot of different interactions. It even goes further. There has been kind of some studies in preclinical and clinical models in the 2000s to show that, of course, the vestibular system will also inform about our direction, movement in space. And it makes a lot of sense, because your kind of head guides you if you move through the environment. And of course, that would mean that you had to have some kind of projections of the vestibular to certain regions in the brain, which are dedicated for heading directions and spatial orientations. And this is essentially the hippocampus, which is the main hub for these spatial orientation aspects. And of course, then the basic researchers started to identify cells which had this very specific response pattern guided by your head direction, called head direction cells in the end. And if you were tracing them electrophysiologically, they would just respond to a certain turn of your head and to the other. This would be the carryover of a physiological signal to a certain cell type, which then builds up a certain spatial representation of the environment. For the detection of these cell lines with others together, there was a Nobel Prize awarded in 2014 to the Moses and O'Keefe. And essentially that was, if you like, the second Nobel Prize dedicated indirectly to the vestibular system after Barani, and this was in the early 19 years. So you see, it's a topic of interest. And you're the next generation to actually decide whether miracles still open. The inputs to this hippocampus systems, of course, is quite multi-synaptic, which makes life a bit hard, because we always are used to tracing maybe one or two steps or synapses, but that is truly multi-synaptic, and it's redundant, and it's not the low-hanging fruit can catch if you want to decipher these kinds of projections. So this is the physiology, if you like, and the anatomy of the central system in a nutshell. And now we are coming to these concepts of central and high vestibular disorders, and essentially they are based on two assumptions. First, if you have lesions which hit these kinds of networks, you may end up with a vestibular disorder, which can be different phenotypes. It can be vertical dizziness, imbalance, and so on. But the second thing is that you may also have vestibular disorders which have a phenotype of another system. For example, room tilt illusion. Room tilt illusion means all of a sudden you feel that you're scenery tilted by 90 or 180 degrees in your visual system, but you're still upright. That is an illusion which you perceive visually, but I will convince you that in the end the problem is vestibular. That makes life a bit hard, that you decipher phenotypes and pathophysiologies. And second principle, which is important to acknowledge, is that along these lines you can have the same phenotype in different locations. And this makes, of course, topo diagnostics hard, and it even goes further that you have to delineate it from peripheral disorders, which clinically is very important. So I'll show you some examples. I don't want to make you an emergency doctor, but just to have a first feeling of how the things look like. If we are in clinics and, acute vertigo dizziness is about the three most common complaints we see in a non-surgical emergency room. It's just a fact. and it means that's extremely common. What we want to see is it a peripheral disorder, as you have seen before, or is it a central disorder? And essentially, you have two phenotypes. Again, this acute vestibular syndrome, where the main aspect is the spontaneous nystagmus, which shows you some asymmetry of vestibular projections. What we see here subtly is that the spontaneous nystagmus may invert direction if patients look to a different side, which would be a violation of peripheral physiology, because a peripheral spontaneous nystagmus would never invert direction. But for this, you needed to have an additional deficit of central networks, which Hermann brought up, of place holding. And only in this case, you have a central phenotype. But it may be you have other patients who are not able to stand all of a sudden, and they just fall and have no nystagmus, which is called acute imbalance syndrome. So the kind of underlying anatomy, if you like, for that is that, these lesions again are homed in different parts of the cerebellum, for example. And, I don't think you need to know all of this anatomy, but just you get the principle. If you have a lesion which essentially hits the vestibular projections, which would be in the medulla, the flocculus, and the nodulus, you'll get a vestibular phenotype like spontaneous nystagmus and falling to one side. If you hit other parts of the cerebellum, which are more dedicated to postural control, for example, the superior parts, but not to vestibular connections, you'll end up with non-directional postural imbalance. And therefore, it's important that we recognize the phenotypes and align it also with your central anatomy. Just one short remark to clinical rules we use for this differentiation is that the situation is you have a patient, acute vertigo, you see the spontaneous nystagmus, and in the emergency, you should just say, is it central, is it peripheral? And these rules which you use actually are taking advantage of the physiology. We translate the physiology to certain clinical tests in order to differentiate the one and the other. As you heard, if you challenge the vestibular ocular reflex, this is harsh movements of the head. You test the peripheral vestibular system in an asymmetric way. That would mean if you do it, turn the head and you get a catch-up saccade, it's pathological. In central lesions, where there already has been integration of both sides, you won't see this. But the vestibular ocular reflex may be normal, even if you have an asymmetric lesion. So that's what we take advantage of. And this head impulse test, which has been described by Hamagin-Kurthos in 1988, is quite a simple kind of reflection of this physiology into clinics. Now, should I show it to you once? Yes. If you won't mind, I'll do it. We'll see. You're on the first row. This is a privilege. So just look at my nose, and what I do is move your conscious in harsh, rapid movements. This is when speed comes in. We have to test that on a high frequency range. Actually, you just look into the eyes. If they are still on target, then the vestibular ocular reflex is okay. If not, it's pathological. This is what we use in clinics. You can do that also with operative quantification. This is a videoculography system. Essentially, it has a sensor which traces head acceleration, and indirectly, via these infrared sensors, also a trace which captures eye movements. And what you do clinically, you can record here. You see what happens in a central disorder, this a bit pinkish and violet trace actually is the head acceleration. That means you turn your head, and it's a peak because you translate the position into velocity profile. It will be a peak now. And normally, as you have a reflex with a latency of 8 milliseconds, your eye would just go in the opposite direction. If you superimpose both traces, they are just the same, and you have a perfect vestibular ocular reflex with again which is the ratio of head against eye accelerations. If you have a peripheral problem, you see here the head still accelerates, the eye does not follow, and then the so-called gain is less than 1, it may be 0.5 here. And at the end of the head turn, you see a catch-up saccade, as you were recognizing, you should look at my nose. And if you vestibular ocular reflex would not do it, you had to catch up voluntarily. This is actually what we do in clinics and also with these kinds of measures to objectify the function of the vestibular reflex. Another thing which, we already touched upon a bit is this, direction specificity of a peripheral and a central nystagmus. Just say that if the nystagmus changes direction as a function of gaze, then it is central. And if it does not change direction, it's peripheral. So quite easy rule. Lately, what we also do is we are looking for these kinds of weird eye movements, which is called skew deviations. It may not easy for you to pick it up with the naked eye because we're also training our physicians there one day off from it. But if you still want to see it, and you always look at the eye, which is uncovered, cover test, you may see there is a subtle catch-up saccade, if you like. Now we'll look into it again. Right eye comes from up, left eye from down, up, down, up, down. It's subtle, but means there is some vertical divergence of both eyes. And this is called skew deviation, and in the end it is a reflection of the so-called ocular tilt reaction. And the ocular tilt reaction is a basic syndromatic finding which we regularly have in central disorders which hit the graviceptive pathways. It means that your perception tilts to one side, this is subjective perception. Then your eyes go into the skew deviation and you have a torsion of the eyes as a countermeasure. And eventually you also have a head tilt. That means that, the brain adapts to this kind of asymmetry by a cascade of eye and head movements. This is happening if you lesion central pathways. We can use this sign to do topodiagnostics. So if you have the lesion down there and the pathways are not yet crossed, then you get it to the lesion side. If the lesion is after crossing, you get it against the lesion side. So it's quite easy to align with site specificity of your central projections. Right, so this is mostly on the acute central part. The issue is not. And now, of course, there may be other disorders which you already heard. We have this concept of acute epilepsy. So maybe that patients come to you to say, we have these spells of vertigo 3 times once, and they last for 5 hours. I always have headaches with it. And then you will end up in this spectrum of so-called vestibular migraine. Again, it's comparably young disorder. St. Prosper Ménière described Ménière's disease more than 150 years ago. The description of vestibular migraine was to the end of the 1990s. That was quite a young disorder, and it's now perceived to be the most frequent episodic disorder across all patients. Another aspect which you see here, and this is what also Vincent touched upon, is that we are not yet very good with capturing this diagnosis based on biomarkers or quantitative measures, but it's mostly the description of symptoms. As you can read here, 5 episodes, 5 minutes to 3 days, a previous history of migraines and accompanying symptoms. And on the one hand, that makes lives easy because you can just by asking patients and doing certain tests make the diagnosis. For research, it makes life harder because you get into a certain heterogeneity and of course maybe a mix of different pathologies which kind of result in a similar phenotype. So biomarker research, if you like, is also a major issue of our field to make more individual decisions. Because, if you could trace it down to a certain biomarker, maybe could also do individualized treatments on the other hand, and this is what WHITE is also about. Just a few side comments to the epidemiology. You know, the vestibular migraine is a disorder of the mid-ages. Females are more affected as for migraine in total. You have a very frequent coupling with anxiety and depression. And you have a second kind of peak in life, which is in children. And I would say that also vertigo and dizziness in children is one of the most neglected fields of our services ever. Because if you ask high school kids, how often are you dizzy, you'll end up with 20 to 30% 1 year prevalence. But, you know, parents will just keep saying, you know, it does not want to do sports. Maybe it's got the next tests to take, it's a bit stressed and so on. So again, a field which I think we need to get more and more insights, and there's a lot of migraine spectrum so for these kinds of young patients. Pathophysiology, you know, in the migraine field, there's been some disruptive results from research. The first, again, from Scandinavia, it seems the Scandinavians have certain masochistic traits to test it on their own. But what one colleague did is that he was taking jugular vein blood during a migraine attack, and then they analyzed proteomics. And a few years later, ended up to find one protein which may always be highly elevated, which is CGRP, a calcitonin-related peptide. And then they put it into animal models. They could evoke migraine-like spells. And then they said, okay, that has to do with pathophysiology with migraine. And all of a sudden, they discovered that this peptide is kind of transmitted by certain nuclei in the brainstem, the trigeminal nucleus complex. And then this was weird German colleagues from Hamburg. You know, they put a colleague who had a migraine every day in the scanner for 6 weeks, just 1 hour. And then she had to indicate when she thought her migraine started. And then they kind of back translated it to the activation patterns of her brain activation. It came out that hours before her headache started, she had activations in the trigeminal nucleus complex. And she had a CGRP peak, and that kind of blew the disorder, if you like. You know, big debate now is the vestibular migraine just a migraine with vertigo, or is it a specific disorder? Not just based on these activation patterns where we have only anecdotal findings, it seems it's not quite the same, because these activation patterns are more to the thalamus and the visual cortices and so much to the trigeminal areas. Of course, we could just repeat this you know, Hamburg experiment with a frequent vestibular migraine to see, you know, if we see the same patterns early on. But that's research in progress. Clinically, you see central signs and symptoms. I think that's not essential. You may have some differential diagnosis. I'm not sure that tone plays actually, because that video. It's not playing, okay.
The sound is down, so if you turn it up, you should be able to. I'm not sure exactly how that will
try to turn it up.
project.
Just hear this kind of guide to
Right. What were the symptoms you had during those days? I had 4 or 5 attacks a day, and symptoms were like I was sometimes completely my coordination of movements, etc. And I couldn't walk properly and things like this. How long did the attack last? So the average, more or less, were there any factors that could induce these attacks or make them worse? Yes, definitely. That's what I found out myself. It was, first of all, drinking alcohol was really bad. Stress.
Okay, so that is just a history taking as we do it every day in the clinic. But this is again on the dynamics, on the triggers, and on the accompanying factors. You know, this patient ended up to have a episodic ataxia type 2, which is a differential diagnosis also for vestibular migraine, but it is a genetically determined syndrome. And these patients, they report they can induce their attacks by physical exercises. So one thing is you just make those patients kind of doing some exercises, and all of a sudden they get really unstable. And in their clinical findings, you see some indications they have also central problems in between attacks, like downbeating nystagmus, for example. Now that's what I just wanted to show you, that we have these actually wide spectrum of diagnoses, which are purely defined by taking. And the other end of the spectrum is we have a heart-blown genetic syndrome, which we can pin down to a mutation in a certain gene. And, anywhere between, I think, we will end up with having modified, individualized therapeutic and diagnostic approaches. And what Sonia is planning here is, the SNPs and MIS genes will be support the approach towards this end of the spectrum. Now, one part of the brain, the cerebellum, got more and more interest also in terms of these genetic disorders. The cerebellum is a wonderful organ, actually, and nobody does understand it fully, so don't worry. What we know is that there are some regions where vestibular processing takes part in the flocculus, the nodulus, and we have some parts of the vermis where eye movements are driven. Cerebellar disorders may be quite frequent also in the differential diagnosis of chronic balance and dizziness syndromes. And just to show you one example of how that could look like, this is one of the most common cerebellar syndromes. It's so-called downbeating nystagmus. The left side is a simulation of what you see on the right side on the patients. It just means if they look into an eccentric position that you constantly have these downbeating of the eyes. So it's obvious that is a central disorder, which has to do with the kind of integration of position signals, etc. And the pathophysiology in the end, which was delineated over the last 20 years, is that these patients do have a hypofunction of these floccular areas again. And this hypofunction leads to a disinhibition, because the cerebellum mostly is a brake, it's inhibiting everything, of circuits of the vestibular ocular reflex, which travel for the superior vestibular nuclei to the oculomotor nuclei, and they support upward gaze. So that means if this system is disinhibited, then you get a kind of drift of the eyes up, which is then kind of corrected by saccadic movements down. Again, pathological is the upward, and corrective is downward. With that, we can actually try treatments, because we know there are some drugs which act on these kind of Purkinje cell-like inhibitions, so-called aminopyridines. And this was a first case where it was shown that after 30 minutes of applying aminopyridines, this kind of drift of the eyes was massively reduced. And it acts via the cerebellar Purkinje cell system. So if you invert the hypoactivation by a drug, you may compensate for the syndrome. And this when it becomes interesting, because we struggled for years to predict who will kind of react positively to aminopyridines and who not. And in 2020, we found with against nucleotide polymorphisms, one gene which was way out, and this was the FGF14 gene in downbeating nystagmus patients. Got not too much awareness this time, but then 2 years later in the New England Journal, they published that the FGF14 was with a repeat expansion gene, one of the most frequent cases of late onset cerebellar ataxia. And just in their small table said that these patients who have it frequently have downbeating. So that is when things converge, and nowadays you can even say that idiopathic downbeating nystagmus is a genetic disorder, which for 3 years from now was not even close to kind of thinking. And even more so, you could predict by the expansion numbers in this gene the response to aminopyridines. If they had a lot of expansions, they responded, and if they had not, they did not. And this is just another example, if you understand pathophysiology, genetics, you may also take individualized predictions, and this ends up to be individualized medicine, what we all strive for, also provide. So just 2 more minutes, Jody, if you allow. This is the high order networks, which of course is complex. And one example which I touched upon a bit was already this so-called room tilt illusion. So patients will say they just see their room shifted over by 90 or 180 degrees all of a sudden. Then all of a sudden it goes away. And, if you look into the lesions which cause these syndromes, you see that the topography of these lesions, again, is various. And just think about why then the room tilts over. If you have a prior which is not really reliable from the vestibular system, and you have a prior from the visual system, and your brain has to take a decision what is right based on experiences and estimates. It takes a decision that likely that room should be shifted by 90 degrees. This is almost an illusion of multisensory interaction, which you get from this. And in the end, it's a vestibular problem. The other side of the medal is that for this part, if you have patients, for example, with a traumatic brain injury, for example, they had head trauma, and then we had a BPPV, but they did not perceive it. They did not feel their eyes were jumping because their vestibular perception was somewhat damaged. And which was shown by Barry Seamundle in London is that they had strategic lesions to certain connections in their brain, which made their perception not functional, after all. This is also what happens with age, by the way. If you have a certain stimulus, maybe that you drive the eyes, but you don't drive your percept. And that means that your patients may refer to their symptoms very differently as if you compare it to a young one. So with that, I think I stop here. Just saying that there is much more than ears and brain stems. Of course, it's important, but there's a lot of brain above it, and that makes our perception, that makes our emotional and cognitive consequences of these disorders. And the vestibular system is somewhere, in the middle of any system. And you could interpret it in a way with novel technology, we can solve it. And, for you, it's important just to see that understanding pathophysiology, genetics, biomarkers, networks really turns into novel treatments. This is what provides value. Thank you very much.